Thanks everyone for coming to this month's Astronomy Fundamentals Special Interest Group presentation. We only have one presentation lined up tonight, and that is on Nebula and their variants. For those who haven't joined us before, normally we give two presentations. We've been doing an astronomer of the month and then another longer topic on something else. Due to some time constraints, didn't have time to get an astronomer of the month in place. So look forward to that next month for those that join us. We're also just kind of running out of additional ideas. I think we've done a lot on a lot of presentations over the last 5 years in terms of things that we can both observe and use with the equipment. So if there's any suggestions, even if it's something we want to revisit, please feel free to email the email contact that was in the Zoom invite, fundamentals@tucsonastronomy.org, and let us know if you have suggestions on things that you would like to see. So gonna go ahead and get started. So tonight, as I mentioned, we're going to be talking about nebulas, the core main types of nebulas and some of their characteristics and a little bit of their history, and have some pretty good pictures going along this way. They are some of the last ones that we've been able to talk about. We've over the last 2 years, we've talked a lot about stars, clusters, star streams, and so it was kind of a little bit interesting to see that we hadn't done anything on nebulas, considering they're one of the more beautiful objects to look at in the night sky, even or to photograph. When my mouse decides to work, there we go. So we're going to look at the four main types of nebula tonight: mission nebulas, reflection nebulas, dark nebulas, and planetary nebulas. There are some other subcategories that go into this as well, which we won't go over because we talked about them loosely during other topics, such as supernova remnants. Are you guys able to hear me okay?
Yeah.
I just have a warning that I'm too quiet. So first off, we're going to start with the mission nebulas. So these, all nebulas, by certain definition, are large collections of gas and dust that can stretch up to many dozens of light years in size and density. So you'll see that kind of is recurring through all of these slides. What distinguishes emission nebula from the other categories is that they are the gas in emission nebulas is being ionized by young bright stars near the nebula. Getting a lot of reconnecting warnings. And the light from these hot young stars, typically O-class and B-class stars, is putting out large amounts of radiation above the UV spectrum, and this causes the gas to ionize. And as the gas wants to enter into, like a lot of things in physics, they like to be in a ground state. They don't like being energized. They will emit photons. And the color of these photons is characteristic of the molecules in which they are being energized. With that kind of a bit of a mouthful there. And so the light from the stars hits this large collection of gas and dust, which causes it to emit light, hence the name. Here's an example of an emission nebula. This is the Flame Nebula, NGC 2024. It's located. I turned off subtitles. Stop. There we go. I was like, I could have sworn I turned that off before I started this. It's annoying. There, everything's bigger. So this is located right next to the leftmost star in Orion's belt, which you can actually see tonight. So then that's on the tack remember correctly, and my stars theorized value origins are right here. So and as you can see, there's kind of the characteristic reds. There's a little bit of these dark spots here, which are more characteristic of dark nebulas, which we'll talk about towards the end here. So this it's officially cataloged as an emission nebula, but it has characteristics of both, which may be more of a common theme. And you can also see that there is a lot of red within the nebula, which is also typically characteristic of emission nebulas. The red, in turn, comes from the light, not the light, the large amounts of hydrogen that are found within these nebulas. The blues, which you'll sometimes often see, for example, for those that may have looked at photographs of M42, the Great Orion Nebula, you'll see that there's also large amounts of blue in there. That's coming typically from oxygen or from the hydrogen beta lines. For those who may not be familiar with that, all the elements, when ionized, they will glow in a certain color that is specific to that element. And so this is what we use to determine the elemental composition of everything in the universe, from stars to nebulas to galaxies. In fact, Hubble itself uses a combination of hydrogen, oxygen, and sulfur filters for most of its pictures. So every time you're seeing Hubble, it's typically a combination of these three elements. Hydrogen is the red line. Hydrogen alpha is the most dominant line in these nebulas, which has led most of the emission nebulas to be cataloged as H2 regions after the hydrogen. Sorry, that should be hydrogen alpha emission line. No, I'm getting hydrogen confused. It's a specific form of hydrogen that this is getting named after, with hydrogen 2, I think, being deuterium. I'm not quite sure. Can't remember off the top of my head. I apologize for that. This is another example of an emission nebula. This is the Trifid Nebula, which is in, I want to say, it's not Sagittarius. I think it's in one of the Serpens. But this is an example of both an emission nebula. Here, there's the red glowing orb that forms the large part, and then up here at the top is a small reflection nebula. We'll talk about more of those in a second. So again, you get this really bright, strong red coloration inside of emission nebulas. These are important for kind of a number of reasons. Because these nebulas are illuminated by these young O and B class stars, and O and B class stars are always going to be young. They have very short lifespans compared to other stars, measured in the tens of millions of years, compared to the billions of years for stars like our sun. Which means that you will almost always find with a emission nebula what's known as a stellar nursery. So the emission nebula itself is often forming new stars within it. So for those who have seen the Lagoon Nebula M8, the Eagle Nebula M16, and the Great Orion Nebula M42 are all classic examples of this. These are all star-forming regions and also all emission nebulas. As part of this, the stars themselves also contribute to the death of the nebula. The ionizing radiation from the young stars is going to push the gas away and cause it to diffuse. And it also inhibits star formation. Star formation can only occur in nebulas and the very coldest, most dense regions of nebulas. And so as the light is pushing away this gas, it inhibits star formation inside of the cluster. And over time, you are left with just an open cluster itself with no nebula. If for those who might have seen the double cluster, this is an example. Their emission nebula has been blown away by the younger stars in the cluster. And so all that's left is just these two pairs of open clusters in the night sky. There are estimates that in an emission nebula, about 90% of the gas will go unused. That's going to spread out and join it into the interstellar medium, kind of mixing around, and eventually, in some cases, it will coalesce into a new nebula over time. So another example of a classic emission nebula here with the Lagoon Nebula. This one is in Sagittarius, and as you can see here, we got this open cluster kind of sitting in the foreground, kind of embedded on top of a larger nebula here. So with some bright stars. Let me do laser pointer, and I'm going to make this purple. No. That is not helpful. I tried to change that. But we have a bright star here and here, and here, and all these bright stars are what's ionizing this gas with the young cluster over here. Moving on from that, we have our next candidate, which are emission nebulas. So again, these are, did I say emission nebulas? I meant reflection nebulas. So these.
Thank you.
Sorry. These nebulas, like their name, instead of emitting light like emission nebulas, they are reflecting light from a nearby star or a cluster of stars. The difference here being that the nearby stars that are illuminating the gas aren't putting out enough UV, right, or higher in order for the gas to ionize and emit light on its own. So the light from these younger stars essentially just bounces off of the gas, and that's what we see. Another thing that aids in this is this gas is typically rich in heavier elements like carbon, iron, and nickel. And this is what helps aid the reflection of this light compared to gas clouds that may be more rich in just pure hydrogen. So this is an example of telltale reflection nebula. You only typically see this in pictures if you look at the Pleiades cluster, which is what we have here. This is M45. You'll see we have lots of dust filaments here being illuminated by the young cluster, all of it glowing this telltale blue. Part of that blue is a characteristic sign of emission nebula. So if you're seeing a lot of blue and not a lot of red inside of the nebula, it's just in pictures specifically, you won't with your eyes see color in any of these nebula if for those who are doing visual observing. But if you're looking at pictures and you see a lot of blue, it's typically a good sign that it is a reflection nebula, unless that person's doing some interesting things with their images, which we won't get into here. So as I mentioned, because the gas in reflection nebula isn't ionized, it tends to be more blue in color. And a part of this is due to the size of the dust grains. It so happens that not only does the composition of carbon and nickel and iron increase the reflectiveness of these nebula, but the grains themselves are conveniently sized that they reflect blue light more efficiently. And this is actually the same process that going on in these gas that we see that makes our sky blue during the daylight, known as Rayleigh scattering. Another important thing is that because the gas of this light is not ionized, it helps. It can be used to help figure out the chemical composition of the star or star cluster that is illuminating a nebula, which is actually something really cool of how astronomers can work back from that to find certain things about objects indirectly. So this is another example of a reflection nebula. This is Messier 78 in the Orion Nebula. I was kind of confused why most sources list this as a reflection nebula, having You guys hear me?
Yeah.
I just had I think something's wrong with my setup. Next slide. It's telling me I'm on a different slide than what I'm presenting. Do you guys see the reflection nebula Messier 78?
Yes.
Okay,
Yes.
I think PowerPoint is desynced on me. We can keep going though. I see one screen that it's showing me something else. But as I've recently been photographing this nebula myself, to me it gives off in my own images the characteristics of a dark nebula, mostly because there's not a lot of illumination going on here. But I suspect that it's mostly due to these two, this region here in the top left, and mostly here in the center, that makes it officially cataloged as a reflection nebula, because you have these bright stars here and here that are giving off that blue characteristic of reflection nebulas in this image. But even in my images, you won't see this. In fact, this is a very difficult target, in my opinion. So in terms of history of where some of these things get named, I wasn't able, as you saw, I wasn't able to get anything about emission nebulas, but the term reflection nebula is actually somewhat newer. We've known about, in some way or another, nebula have been cataloged in the night sky since William Herschel and Charles Messier, even if Messier didn't explicitly call them nebula in some of his catalogs, but more non-comet regions. But the reflection nebula was coined by astronomer Vestos Slipher in 1912. So in the 20th century, while he was conveniently studying the Pleiades. As part of that, Edwin Hubble also comes into this picture in terms of telling us a little bit more about reflection nebulas, where as part of his work, while he was studying what was at the time known as nebulas, but we now refer to as galaxies, he devised a mathematical formula, which is shown here, that organizes, how the visible magnitude of the star or star cluster, with how bright and wide the reflection nebula is, which I thought was an interesting relationship, and also a very simple one, where you just have the apparent magnitude, the radius of the nebula, the apparent magnitude of the parent star, and a measurement constant, which we won't get into. It's sciencey. But like also, so I thought that was just kind of really cool, seeing Edwin Hubble show up again here when I wasn't expecting him to. But another thing that's common with these nebulas is, like emission nebulas and dark nebulas, as we'll see, these are also typically star-forming regions. So they may just be in a much earlier stage of star formation compared to emission nebulas. I wasn't able to find a direct progression, but from looking at a lot of picture examples, you can kind of see that reflection nebulas typically are a lot darker. As we kind of saw here, there's a lot thicker dust filaments compared to emission nebulas. And so my initial assumption is that emission nebulas are a reflection nebula will in many cases progress to an emission nebula over the lifetime as stars are formed within it. Any questions so far? Any comments? Cool. So from there, we're moving on to dark nebulas. We'll kind of hit on them a couple of times already. These have an alternative name. They're one of the often referred to as absorption nebulas, which is both technically, I kind of give you a hint about, the main characteristic of these nebulas. They are very dense compared to reflection and emission nebulas. So dense that they're basically opaque objects, and they don't allow light to pass through them. So they essentially just look like really dark regions of space where there's nothing there, because no visible light is able to pass through them. Other wavelengths, notably infrared and radio waves, are able to pass through, which, as if some have seen more recent images from James Webb, which does work in the infrared region, you can see examples of it in the pictures that it took of the Carina Nebula and of the Eagle Nebula, even those two aren't dark nebula specifically. Part of the reason for this is that these nebulas also tend to be rich in carbon monoxide and nitrogen, which amplifies their opacity, makes it a lot harder for light to pass through them. Also of interest is that these are used in building blocks of primitive organic molecules. So these you will occasionally see some papers refer that some of these nebulas contain large volumes of simple alcohols, which you can then insert a whole bunch of party jokes, and you could get drunk off of them and never ever have to worry about it. These, because of their density, these are also some of the coldest regions in space. There was a recent nebula. I think I'm getting ahead of myself on a slide. I think if I don't have another slide ahead of me talking about this, I'll circle back on it, on the temperatures thing. Even though we've said that these nebulas are quote unquote dense, you're still very sparse with these nebulas are still less dense than the air we breathe, with about 100 to 300 molecules per cubic centimeter. Yes, Pete.
Yeah, kind of going back to the second statement there, as far as the absorption or the dark nebula blocking most of the visible light, do they still block a certain amount of the radiation at the other wavelengths? For instance, are they still blocking some of that infrared, even though some of it's getting through?
It depends on where the infrared falls, because you have near infrared, far infrared, and mid infrared.
Right.
So off the top of my head, without having seen anything when I was making the presentation, I would say that they would be probably blocking some parts of the near infrared spectrum, which may be closer to the hydrogen alpha emission, one of the hydrogen emission lines.
Yeah, because I guess the whole point is, the whole point of my question is, if there's that much matter, it's going to have an effect at just about every wavelength that's just said. I would imagine certain wavelengths, like visible light, are impacted more than others.
That's correct.
Okay. Is there a nice little formula that probably tells us that, or?
There may be a formula, but it's probably not a nice formula.
It's not a nice formula. I've seen it in some of the more advanced astrophysics book when I was in graduate school. There are some formulas for how to determine how much radiation gets through at a particular wave, dependent on the content of the cloud. Different chemical compounds block different amounts, but there is a formula for that'll give you the for the wavelength, how much gets through at each different wavelength. But like Connor said, it's not a nice formula. It's a nasty formula that takes up a whole page of.
So it's not just the density of the matter that may be blocking certain wavelengths. It's also the elemental composition.
Yeah, okay. Absolutely.
Yep. Very good. Okay. Thank you.
Good. Because as I do say here, with the carbon monoxide and nitrogen amplify the opacity. So depending on elements,
any of those carbon compounds really block the visible light big time.
So to kind of equate that, for those who maybe follow any of NASA's research that they've been doing with asteroids and the asteroid belt, may know that carbonaceous asteroids are very dark.
That's right.
You cannot see them. they are almost exclusively found by using radar
Yeah,
because they just absorb so much light.
the albedo on those things is so bad.
You know, if you think of charcoal, carbon is almost pitch black, so it
Yeah.
just absorbs light like a sponge and doesn't let it go. So kind of the same thing going on there. So this is the Coalsack Nebula in the southern hemisphere. Fortunately, we cannot see this from Tucson. Kind of is an example of a dark nebula, excuse me. So you got what it almost looks like you're staring into this void of stars here, right in the center, and also kind of here off to the side. So this isn't empty space that we're looking at. This is just all the light from the stars, and there are a lot of stars in this picture. If someone wants to spend the next couple of hours counting with me, by all means. But you can see that a lot of these stars are just blotted out because there's gas in front of these stars, which is blocking their light from reaching us. Like reflection, I mean, they're actually only more recently cataloged. And I actually want to do after looking at some of the work that Edward Bernard did while making this presentation, I want to do an astronomy profile on him, but I'll probably have to wait till I finish the semester. But dark nebulas were formerly cataloged by Edward Bernard in 1919. Edward Bernard is an American astronomer, but I won't get much more into that. If some of the nebulae you may know in the night sky are cataloged, still bear his catalog designation. I have a picture of one coming up that we all probably are familiar with. And these dark nebulas contain much of the mass in the interstellar medium that's not in a star. So if you've seen pictures of the Milky Way and you see all these bright dark spots and long trains like the Pipe Nebula, all of that is dark nebula. So almost a great portion of the Milky Way that we see is dark nebula, just to give you kind of an idea of just how much mass is in these objects. And I knew it had it on a different side, but as I mentioned, these are some of the coldest regions in space. The Chameleon 2 Nebula, I think it's Chameleon 2, 1 or 2, was recently found by James Webb to be about 10 degrees above absolute zero. So as I also kind of touched on a little bit earlier, this cold temperatures lends them well to star formation. So it's a constant theme here. Most of these nebulas are related to star formation and are essential for the evolution of galaxies and our own solar system. And so as the stars form within this cloud from these very cold and dense regions, it will move on and transition into an emission or reflection nebula, which is kind of what we saw in that picture a few slides back with M78. It has some of those really dark, knotty regions and then some portions of a reflection nebula. So you kind of get a sense of where these nebula kind of evolved to over time. Of course, not necessarily on human timescales. So this is an example of a dark nebula. With Barnard 33, also known as the Horsehead Nebula, which is right next here to the Flame Nebula, which we saw earlier. Focus on this isn't as great as I would have liked, and there are better pictures out there, but it's kind of giving you just this compare and contrast between you have this dark nebula portion here that forms like the giant pillar in the Horsehead that we're all familiar with. We got a little bit of an emission nebula behind that. An emission nebula over here off to the left with the flaming nebula, and so it kind of blends itself well. So Barnard was the first person to officially categorize and catalog many dark nebula. I believe he cataloged close to 300, and most of those dark nebulas were only found by photography. Because you just needed that. You won't be able to see a lot of these, with some exceptions, well without the aid of photography. And last on our list, we have planetary nebulas. So these, even though they're technically a subtype of emission nebulas, they deserve a little bit more of a special call out, which is why I included them on here, and didn't include things like supernova remnants. So these nebulas are remnants of sun-like stars. So stars between a little bit between the size of the sun up to about 8 solar masses. And these stars have reached the end of their life and they've blown off their outer layers and they've turned into white dwarfs. And so this blown off outer layers of these stars is what forms into the planetary nebula. And in pictures, you will often see that these have a very great variation in colors. This is because the outer layers of these stars are formed through the various types of fusion of hydrogen into helium, into carbon, into oxygen, and into nitrogen and iron. So that smorgasbord of the onioning going on in their outer layers is what contributes to their very varied coloration and also their distinctive shape. So during the process by which these stars blow off their outer layers, this releases also a large amount of UV light, which provides the illumination for the gas. And like over time and on much shorter timescales compared to the other 3 nebulae we talked about, these planetary nebulas will dissipate because the white dwarf will cool over timescales, and it will no longer emit enough UV light or X-rays, or in some cases gamma rays, to ionize and provide energy to the gas. And so it'll slowly blend its way back into the interstellar medium. So this is kind of an example here. This is the Helix Nebula. That should be image credit to NASA, not the NAA. That is a typo. Also known as NG 7023. This is, for those of you who are interested in looking at this, it is a fall object, best viewed between September and November. I know because I keep trying to photograph this object and I keep not getting a picture I really like on it. It is one of the largest planetary nebulas that, no, it is the largest planetary nebula that we can see from Earth. It is about 2/3 the diameter of the full moon, so it's about 20 arc minutes, making it very big. And you can, even on very short exposures, you can see distinctive blues and greens, not blues and reds within this nebula, and also even a hint of green. And then all of that is provided by the illumination of oxygen, providing a lot of the bluish green, and hydrogen providing the red, which is, you know, a common color combination, as we've kind of hinted on here. So the naming for planetary nebulas actually comes from French astronomer Pollux. I'm not going to pronounce the rest of his name because I will get the middle of it really butchered, which came from him as he was studying the Ring Nebula, which is another example of a planetary nebula, which we'll talk about here, in 1799. William Herschel also kind of helped lend credence to this name, where he was observing what the Saturn Nebula, which is a nebula, despite being, is a planetary nebula, both name and in statement. So I called it a planet of the starry kind in his notes. As part of Herschel's work, when he was working on the NGC catalog, he cataloged many other types of planetary nebula. But we now know that most of those he ended up cataloging are actually.
No.
Can you guys hear me?
Nothing.
Okay, thought I lost audio for a second. But we now know that most of the nebula that Herschel ended up cataloging weren't planetary nebulas at all. They were galaxies. But we didn't have the ability to distinguish them or recognized that they were proper galaxies until here in the 20th century with work that was done by Hubble. So this is another example here of why these are sometimes mistaken. Well, where initially got their name. Most of these nebulas will look into the telescope, look kind of like a ball of gas, a very small dot. Another example of this would be the Cat's Eye Nebula, which is, I think, in Draco. Showing this, you'll get like this little small, really dense puff that makes you think you're looking at a planet. Even visually, if you, for those that have seen the Ring Nebula visually through their own telescopes, you're just like, oh yeah, that does kind of look like a really small planet because it's like really puffy and very small. Planetary nebula are important because they are one of several possible ending states for stars. So stars will, when they reach the end of their life, they will typically die in one of several ways, the others being neutron stars and black holes, the other being white dwarfs and planetary nebulas together. This ending state turns out to be really important because they are responsible for seeding a lot of the lower mass elements in the universe. So it's almost very likely that all of the organic molecules in your body came from one or more planetary nebulas at some point. And with other heavy elements like the transuranic elements, gold and silver being provided by neutron stars and supernovas. What's beneficial about this is these nebulas have a lot shorter lifespans compared to other nebula, just that they blend it so thoroughly and leave so much. But there are only about, I think, 3,000 planetary nebulas that have been formally cataloged within the Milky Way. So despite having a lot of stars that are, I think it's like 25% of all stars in our galaxy are within the range of mass of the sun, or within like 1 to 8 solar masses, you would think that there would be a lot more planetary nebulas. But because they white dwarfs are cooling over time and dissipating, a lot of them are just have dissipated and we can't see them anymore. So here's kind of another example here. This is the planetary nebula NGC 2438 within Messier 46. So the open cluster is here in this background area, and we can kind of see here this planetary nebula here. That's all I got. Any questions or anything? Anything that you felt lingering that maybe I didn't quite address, and maybe I might be able to answer because I didn't think to put it on the slides.
Well done. Thank you, Connor.
So
I have a question.
go for it.
Was our solar system once a planetary nebula?
So planetary nebulas are the end of a star. So the sun will so the sun right now is in what's known as the main sequence phase. Eventually it will transition into a red giant. And then after a certain point, when it no longer has enough fuel to maintain that state, then it will turn into a white dwarf and a planetary nebula. But to answer the other half of your question, the sun was at one point part of an emission nebula or a reflection nebula. And there's some kind of debate. There's still a lot of debate in terms of like where exactly in our galaxy the sun itself formed, because we haven't found, to my knowledge, it might have changed because it always is, any stars with similar chemical compositions to the sun that would indicate that they would have formed out of the same nebula as the sun. So we still don't know a lot about where the sun itself formed in our galaxy. There was also one hypothesis that the sun might not have formed in our galaxy. It might have formed in a galaxy other than the Milky Way that collided with the Milky Way and merged with it. But I don't think there's any evidence to back up that particular hypothesis that I have seen.
I'll continue that discussion just a little bit. Part of the problem with trying to figure out where the sun formed is that the sun is 4.5 billion years old. It has made several complete rotations around the galaxy as it goes around the center of the Milky Way. It's made several complete rotations, and any cluster of stars or nebula that would have been present at the time the sun formed has probably been totally dispersed.
Right. It could also be to that point as well that any sibling stars with the sun may be on the opposite side of the galaxy, and we just
that's
can't see through it as well.
What I mean is they're probably the whatever cluster we were in when the sun first formed is probably spread all over the galaxy by now.
When I heard dispersion, I thought you were referring to the nebula we formed out of, not the star cluster, not the open cluster itself that we would have at one point been a part of.
Yeah, the nebula is long gone by now.
Yes. So, any other questions or comments that people want to add into the conversation?
So I have a couple ideas for topics that we can talk about, so I'll send an email to you.
Thank you, Doug. Cool. And with that, thank you all for coming. As I mentioned, we only had the one presentation for tonight. And I do apologize. I would have liked to have had two, but I just got too busy with school. So I'm gonna